In this video, I want to introduce the idea of Gauss-Jordan reduction. Gauss-Jordan reduction is a process to take a system of equations, like the one we can see on the screen, and transform it into a series of equivalent systems, other systems that have the same solution set, until we get to a point where we know the solution to the system. In this video, I'm not going to go through the details of how to solve this problem. There's a separate video where I take this problem and I go step by step using the process of Gauss-Jordan reduction and I solve it. There's a link to that video in the description. What I want to do right now is talk about the big picture, an overview of Gauss-Jordan reduction, what we're trying to do, and the big picture, how we actually go about doing that. So remember, when we have a system of equations like this, we have elementary operations. These are things that we can do to the system that won't change the solution set. So what are our elementary operations that we can do to solve this system? Well, we can always switch to equations. If we switch where two equations are, that definitely doesn't change the solution set. We can multiply an equation by a non-zero constant. And the final thing we can do, which is, I think, the most interesting one, is we can take one equation and multiply it by something and add it to another equation. So we can add a multiple of one equation to another. And what we want to do with Gauss-Jordan reduction is have a process by which we can look at a system of equations and know exactly which of these operations to do so that we don't have to just guess that something is going to help us. All right, so what is our big picture here? The first thing we're going to do in Gauss-Jordan reduction is we're going to get rid of a lot of things that always show up and are kind of just in the way. And that's these equal signs and these variables. If I go through solving this system of equations, there's not really a point in rewriting these all the time. So I'm going to turn this into an augmented matrix. And what a matrix is just a rectangular array of numbers. So I'm going to take all these numbers and I'm going to put them in a matrix. Now there are different ways to write a matrix. That is, we can put various things. We'll put a vertical line here to separate our coefficients from the left-hand side from the right-hand side, and I'll just write brackets on the outside. You can also write open parentheses on the outside. That's fine as well. We'll turn this into an augmented matrix. So what I've done here is, for instance, this first equation, 6 times x2 plus 18x3 plus 12x4 equals 0, I've written all the coefficients down as the row 0, 6, 18, 12, 0. So this 0 is the coefficient that would have appeared on x1 if we had written it out. And so I convert my system into an augmented matrix. And then what I'm going to do is, instead of doing these elementary operations on equations, I'm going to do the elementary operations on the rows of the matrix. I'm going to do a series of elementary row operations. And what are these row operations? Well, I can switch two rows. That corresponds to switching two equations. I can multiply a row by a non-zero constant. That corresponds to multiplying an equation by a non-zero constant. And then the final thing I can do is I can add a multiple of a row to another, which corresponds to adding a multiple of an equation to another. So these will be my three types of elementary row operations. So I'll go through a series of elementary row operations, and once I've done that, I'll have this turned into a matrix that's in echelon form. Remember, we had this notion of a system in echelon form. We'll have a very similar notion of a matrix in echelon form, where it has this sort of stair-step shape. And don't worry about where I got these numbers from. Again, there's a separate video where I'll walk through how to actually perform this, how to find these numbers. So I do this series of elementary row operations, and now I have a matrix in echelon form, remembering that means that we have this sort of staircase shape, right, as we go down and to the right. And we'll actually even go a step further. We'll say, look, we can do another series of elementary row operations. So more row operations. And we can actually get this matrix into an even nicer form, which is known as reduced row echelon form. And so for this matrix, we'll end up with something that looks like this. And what you'll notice is this matrix is still in echelon form. It has the same echelon shape, but I've added a bunch of zeros above the ones, above the leading variables. And what we'll see is that this allows our system to be really easy to solve. So I can now take this system and say, okay, well, from the bottom row, this tells me that x4 is -1. This next row up tells me that, I should write this kind of spaced the way we had it. This next row tells me that x2 plus 3x3 is 2. And the top row tells me that x1 plus 23x3 is 16. So this is a really nice system because when I go to solve this by back substitution, well, we already have that x4 is -1. x3 is a free variable, right? It's not a leading variable. And so I set x3 equal to a parameter. I'll choose x3 equals s. And then when I move up to my next equation, x2 plus 3x3 equals 2, I can replace x3 with s because that's what it equals. And I get that x2 is 2 minus 3s. And then finally, I move up to the top equation. x1 plus 23x3 is 16. x1 plus 23s is 16 because x3 is s. And finally, x1 is 16 minus 23s. And putting this all together in order, I have the solution to my system of equations. Again, I skipped a lot of steps. I wasn't intending to show you how to actually go through this process. But the big picture is that what we'll do is two main things. We'll work with matrices instead of systems. This is efficient and it's going to be nice because it translates everything into stuff that we'll use over and over again in other situations, not related to systems of equations. And we'll use elementary row operations to first transform our matrix into echelon form, and then to go even further and translate it into reduced row echelon form. Which we'll often write RREF, just to save time writing, from which, in reduced row echelon form, we can really quickly write down our solution set. So again, there's a video linked in the description where I'll actually go through this process and explain what are these row operations. And more importantly than what they are, how do I choose them? Because that's the big point of this algorithm. we'll have a nice way of choosing these operations so that we're not guessing and so that we know what we're doing will take us to a solution.